Good morning, ladies and gentlemen. Welcome back. This is Mr. Chen for another quick lesson on MCR3U, Functions 11, Binomial Theorems. And today we're going to be looking at the binomial theorem in Pascal's triangle. And the basis behind this is to expand relatively easy. So what you see in front of you is the package that was given out in the Google Classroom. And again, feel free to pause the video if you need some help. I'm just switching my tablet now to make sure I can write properly. So for the first question here, I do recommend that you try to do it. You don't have to do it all. And again, you might want to just watch. But it's just the understanding, first of all, of what the binomial theorem or binomial expansion is. So if we have a binomial, let's just say a plus b to the 1, we can definitely expand the second one, a plus b all squared. That is what's called a perfect square. And we get a squared plus 2ab plus b squared. Now, questions C, D, and E, we really haven't really done these ones before because they're higher order, right? This question 1b, it's a quadratic, and so it's a perfect square, and it's all good. The second one, or the third one, 1c, it's a cubic, right? And so the way to expand this traditionally, you can actually understand that's a plus b times a squared plus 2ab plus b squared. And the reason why you know this is because this is actually a plus b all squared. One more time as a refresher of your exponent rules. This base multiplied this space, there's a 1 there, and you can add their exponents, and that's why it's a plus b all cubed. So really what you need to do for this, and let's just highlight with some colors here, there's no acronym for this, it's just really distributive property. We have to distribute the a across those three terms. And so what we get is a cubed plus 2a squared b plus ab squared. Now hopefully if you pause the video, you can actually do the distribution of the other term, the b in this binomial, and you'll distribute it like so. So let's see if you can continue to do that yourself. I'll pause for a second. And then we'll continue on. So that is going to be a squared b. Notice we tend to put alphabetically the a before the b. It doesn't really matter, but I just don't want to confuse you in this lesson. So the next one's going to be 2ab squared. And the last one's going to be b cubed. Now we're not finished yet. A lot of you realize there are some like terms to collect. And so we got 2a squared b and this a squared b. So that's 3a squared b. And the ab squared and the 2ab squared, they're also the like terms. That's again 3ab squared. Notice when we collect like terms, we simply add or subtract the coefficients. And then finally we get b cubed. So there you have it. We have a cubed plus 3a squared b plus 3ab squared plus b cubed. And I'll be honest with you, most students do not memorize this. So question D, what? You have to do a plus b to the fourth. Does that mean we're going to do this? A plus b times a cubed plus 3a squared b plus 3ab squared plus b cubed? Well, you can, but we're not going to do that. So we're going to come back to this in a moment. And hopefully you realize from this question here, and I'll highlight again in blue, with a plus b all cubed, there are 4 terms. A cubed plus 3a squared b plus 3ab squared plus b cubed. So I'm going to just skip through the package here just a little bit. And although question 2, how many terms are in the expansion, blah, 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 you can keep on doing that. Study the terms of each of these expansions. Describe how the degree of each term relates to the power of the binomial. Now, what we have here, let's just zoom in a bit more in detail. Scroll up. We'll use different color here. Maybe we'll use green. For question 4, hopefully, I cannot remember, maybe I did or maybe I didn't. In the previous lesson, I showed actually how to generate what's called Pascal's triangle. Blaise Pascal was a fantastic mathematician and chemist, and that's why he's related to a lot of the chemistry terminology and related to their units. Nonetheless, as a mathematician, he's not the only one. In fact, famous Persians, the ancient Chinese, Arabic, actually discovered this particular patterning system. But in the Western world, we tend to attribute to Pascal, and this is called Pascal's triangle. And I'm actually going to generate, even though you can see the answer right here, I'm just going to start it off. So it's a little bit easier so that you can see me walk through it. The first number of Pascal's triangle, we always start with 1. And notice the next row is going to be a 1 and a 1. And look how I wrote it. The third row is going to be 1, 2, 1. And hopefully, you can think of maybe a pattern that might be generated to get to this point. The next row is 1, 3, 3, 1. And the next row is, hopefully you can already predict it, even though the answer is over to the right, it's going to be 1, 4, 6, 4, 1. And the reason why we get there is I think some of you can see it, and I'll draw it with a different green, that this 2 was generated from 1 plus 1. If you take a look at this 4 was made up of 1 plus 3. So it's kind of recursive, it's kind of related. In fact, we would say it is recursive because we don't tend to generate, like I can't find the 7th row without actually building this up. All right, so let me just erase some of the green here, if my erase will work, just so we don't just clean this up. So a lot of you realize this pattern, there's a reason why I'm talking about this now. I said to you, let's just say I want to find the 7th row, right? What is the numbers of the pattern for the 7th row? Well, a lot of you realize this is the first row, and this is the second row. Let me start again. This is the first row. I'm going to call it n equals 0, and then we'll call this n equals 1, and then we'll call this n equals 2, this is n equals 3, n equals 4. So I asked for the 7th row, right? We might not have enough room, but let's see if I can fit it in. So we'll use different green because even though I am using green there, let's try to get this answer. So we're going to get 1, 5, 10, 10, 5, 1. And then we get 1, 6, 15, 20, 15, 6, and 1. And they get 1, 7, 21, 35, 35, 21, 7, and 1. So there you have it. The 7th row is going to have those terms, 1, 7, 21, 35, 35, 21, 7, and 1. And what you're supposed to be getting out of this is that Pascal's triangle helps determine the coefficients of the binomial expansion. And so what do you mean by that? How do we get that? Well, let's go back a couple steps and let's just zoom out so it's a little bit easier. Remember our second example, a plus b squared. Let's take a look at the coefficients. The coefficients happen to be 1, 2, and 1. And let's take a look. Where's the 1, 2, and 1? Well, it happens to be right here. So maybe it's a neat little pattern. Well, let's take a look at our blue one. What are the coefficients? 1, 3, 3, and 1. And from Pascal's triangle, can you see the 1 through 1? I think you can. So in a nutshell, basically, some students might think it's harder, but it tends to be a little bit easier. It's just a little bit shorter, just a little bit. But we use this particular pattern to figure out the coefficients and the variables. So let's predict the terms in the expansion of a plus b to the 6. So I think a lot of you know which row we're supposed to look at. And let's talk about some things here. Notice, even though question 1a went a plus b to the 1, what would a plus b to the 0 be? Well, that's 1. And where do you see a 1? Right here. So that's why I'm trying to show you Pascal's trying for the rows actually help us determine the coefficient. Now, there's something actually with the diagonals or the slants. We're not going to talk about that. If you want to know more about that, you can. So let's predict the expansion of a plus b to the 6. So question 5, we'll do that really quickly. So firsthand, what we're doing is we're not really memorizing. We're just patterning things out to figure out the general equation of a binomial expansion. And we'll obviously make this a little bit harder because some students, they say, well, this is not too bad. If it's always a plus b, it's not a big deal. And then this example, question 5, a plus b to the 6, I think everyone is agreeing we're going to look at the 6th row. So I'm going to first write in the coefficients, and that's going to be easy. 1 plus 6 plus 15 plus 20 plus 15, I'm running out of room, plus 6 plus 1. They should all be in a row, but I'm trying to give us the spaces, and there's a reason why. It's because some of you are aware that the variables need to be put in. So let's just erase this portion here as I go back up to the screen. This question D that we didn't really do. I'll just erase this. And let's just take a look at our answer from question 1C, specifically the variables. Let's just zoom in. So ignore the coefficients right now. Let's look at the variables. For the variables, I think we have an a cubed, then we have an a squared, then we have an a, and then we have no a. So it's 3, then 2, and then 1, and then none of a's. So then how about let's take a look at the b's. The b's, well, in this case, now let's go from right to left this time. So this one, there's 3 b's. In this case, there's 2 b's. There's 1 b, and there's no b's. It's a number of b's. So some of you are already noticing a pattern here, right? And this is how you're going to get established. So figuring out the general form. So not only does binomial expansion require you to use Pascal's triangle for the coefficients, we also need to figure out the pattern for the variables. So I think some of you are going to understand what I'm trying to do. When we go back to this question 5, predict the terms of the expansion of a plus b to the 6. So the very first term, I think everyone's okay with, it's going to be a to the 6. Notice how I'm going to think of this right now as a teaching tool. By no means do I really do this separately, but as a teaching tool, I'm just going to show you the pattern. The next term, which has a coefficient of 6, and I said ignore the coefficients, but I'm just trying to get you to look at where I'm writing. This is going to be a to the 5. Notice what the next one's going to be. A to the 4, and you follow the pattern a to 3, a to the 2, a to the 1, and then no a for the last one. I'll just put a line underneath. I will erase it at the end. So those who are dealing with the a's. Hopefully you understood that. For the b's, notice what I said to you. Go from right to left. So again, it's going to be b to the 6. Now again, some students might not understand how I'm getting the 6. So like, how did I get that? Well, look at that exponent, right? So that power is going to be affecting those variables. And if you don't believe us, you have the proof again from our second example there, right? Back to this. So going from right to left, the second last term was 6a. I think a lot of you know it's going to be 5. And that's b4, b3, b2, b1, and then no b. And there you have it, ladies and gentlemen. You have the general expansion for a plus b to the 6. So if you go to the next page of the binomial expansion, this package definitely shows you the correct way of actually doing it, and that some students get intimidated with this format. So don't feel bad. So this is the official. But I'm going to just sum it up for you. Use Pascal's triangle. For coefficients. And then use the pattern to descend for A. Use pattern to ascend for B. So these examples here, and again, note the notes here actually tell you specifically. I think you can read that yourself, but I think some of you get intimidated by looking at the theorem here. So we're almost done. We're just going to do one question, and I think you should be okay. Let's just do question F. I mean, if you can do the first from A to L, really, you should be able to do all these questions here. But they get a little repetitious, and some of the harder ones, like questions 2 to these ones, I mean, you can definitely use it if you want, but I don't want to overwhelm you. Most of the idea is hard enough as it is by just doing the first, what is that, 12 questions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12 questions. I got it. So let's just do question F together. Now let's see if I can make up a new screen, because I don't have enough room here. Well, maybe I'll just do it down here. So question F we're going to do. Okay, because the reason why I'm not going to do the whole thing, but I'm going to first set it up so that you can see the answer. So question F is x squared plus 1 to the 7. So the first thing we're going to do is we have to generate first of all Pascal's triangle. So I like getting that out of the way. If you screw this up, unfortunately, then this tool is going to be a disaster. So you always start with 1. And again, if you're not too sure what happens next, because some students do, unfortunately, 1, 1, 1, they put these 3 1s there. So just be careful about that. And again, if you really want to see it, there's actually zeros on the outside. So 0 plus 1 is 1. 1 plus 0 is 1. So that's why that's where it gets from. But then we don't like seeing all the zeros in math. Back to this. So what we have to keep on going is 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and then 1, 7, 21, 35, 35, 21, 7, 1. I think that was actually the one we actually did. And we could definitely check. Let's check because, yep, you have it. So that's the answer. Now, let's just do the first 4 terms. So we're only going to get the 1, 7, 21, 35. The reason why, if you can do this, you should be okay, right? So even though it's x squared plus 1 to the 7, we still want to have the general expansion for a plus b to the 7. And so hopefully you're following along with me and try it yourself. The general binomial expansion for a plus b to the 7 is a to the 7 plus 7a6b plus 21a5b squared plus, and I still ran out of room still, 35a to the 4b cubed. And it keeps on going. But if you can do this, you should be okay. So this is now why you're going to use binomial theorem by using Pascal's triangle and the patterning of the variables all at once to solve this question 1f. And let's take a look at it. The a is x squared and the b is 1. So we're going to do a quick substitution using this formula that we just actually problem solved. Go through it slowly, take your time. Notice the first term is a to the 7. So x squared to the 7. Then we have, notice I put plus because it's always addition there. The 7 coefficient, let's put that in red because I think we were using red before. And then we have, oops, I wanted to keep it consistent. Sorry about that, ladies and gentlemen. The palette is taking up our time. So let's do it. X squared to the 6. Notice there was a 6 there. And it's still being multiplied by the b value. And what's the b value in this case? This time I will use the color so you can see it. So that's 1, because that's b. I think I used purple. Let's just double check. Yeah, I think I did. Oh, I know I should switch it. I don't want to confuse students. So let's just get rid of that one. This one. Let's try that again. So I'm just using different colors, ladies and gentlemen. Sorry, I'm just trying to be consistent with the colors. So I think, what did I say? Purple, right? So this is 7. So this is 6. And I think we used light blue, yeah, for the B. Let me just double check one more time. Yeah. So now that I have my sample, I won't mess up. Plus third term. Notice the third term is here, and I'll underline this one with 3 lines. So I guess I should have done this one too. 21, and again, we choose red. Because that's where we got it from the Pascal's triangle. And then go back to black. Still x squared. Notice we're not finished. We're just taking our time and making that 21a squared 5. So x squared to the 5. And then we got the blue, sorry, 1. And notice that's a b squared. So that's going to be squared there. And a fourth one is going to be plus 35 x squared to the 4, and then the b, or the 1, cubed. And again, clearly there's more terms, right? There's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 terms when we fully expand this x squared plus 1 to the 7, but we're not going to do that because if you can follow this along, you should be okay. Now, here's what you're going to be doing. And let's just scroll back up to, let's use orange. So even though we use Pascal's triangle for the coefficients, use pattern to descend for A and use pattern to ascend for B, use exponent rules to expand. What does that really mean? So in this example here, we are basically using the power rule. Oops, let's erase that again. M to the A all to the B is equal to MAB, right? So we learned that from our exponent unit. So in this case, x squared to the 7 is x to the 14. Then we rinse and repeat. 7, that's going to be 7. X squared to the 6 times 1. Anything times 1 is going to be 1 itself. So x to the 12. And then we keep on going. 21, that's the coefficient. And x squared to the 5 times 1 squared. 1 squared, of course, is 1. So that's going to x to the 10. And finally, for our example, because I said I don't want to do the first 4 terms, 35x squared to the 4 times 1 cubed, which is 35x to the 8. And it keeps on going. But this is the answer for this expansion. And the reason why we teach it this way is because the traditional expanding and collecting like terms, especially for a higher order, is more prone for incidents of not collecting the like terms carefully, and it gets a little messy. So that's what I wanted to show you with those ones. Let's maybe try one more just to showcase the illustration. This time, maybe we'll do question 1G. And I'll do it in blue. That's x squared minus y squared to the 5. So we'll do it on here. So we already have our Pascal's triangle. But you know what? I'm just going to do that for the first 3 terms. And this time I'll use red. So what did we have to do? I think you guys remember. We need, first of all, the general expansion for a plus b to the 5. And this one's actually easier than the one we just did. I think you know it's a to the 5 plus 5 a to the 4b plus 10 a cubed b squared. So this one's not too worrisome with coefficients. And again, maybe I should have chosen another one. I don't know. Let me just take a quick peek one more time. It's too late. I already started this question. Like J, K, and L, they're clearly hard. I think you'll figure it out what's happening if you go slowly. But let's just do it here for this one. Oops, I said blue. So let's just do blue. So what is the first term? X squared to the 5 plus 5 x squared to the 4. And notice our b is negative y squared plus 10. Oops, not a squared. I made a mistake, ladies and gentlemen. I made a mistake here. Let's try that again. X squared cubed, and then it's negative y squared squared. And it keeps on going. So I just want to do the first 3 terms. And the reason why I'm showing you this one is because the binomial actually has a subtraction. Addition, there's no problem, but with subtraction, you have to be careful. Not always, but you know. So then now we have to use that orange rule over there, power rule. So x squared all to the 5, that's x to the 10. Notice I got to not so quick. The coefficient is 5. The variable, first of all, x squared, y squared, x squared to the 4 is x to the 8. But that negative y squared, that is still going to be y squared, but we tend to put the negative in front. And adding a negative is subtraction. And then our last one, the coefficient is 10, and that's x to the 6. And then negative y squared, when you square a negative, it becomes positive. So positive times a positive is positive. That's why I put positive there. And then y squared to the 2, that's going to be y to the 4. So you're going to see an oscillation of positives and negatives in this answer. But there you have it. Those are the first 3 terms of question G. So there you have it, ladies and gentlemen. There are answers here. And if you have any questions, feel free to contact me by email. As always, try your best, refer to the notes. You'll have the CEMC courseware, and I think you'll find success in our last and final unit. After this, there will be some supplementary work on the financial math, but I don't think I'll have any more additional videos. As always, have any questions, let me know. Have a nice day. Take care. Bye-bye.